Welcome back to our series on the math that makes machine learning tick. So last time we dug into how a model actually measures its own mistakes using something called a cost function. Today, we're taking the next crucial step. We're asking, once an AI knows its cost, how does it actually fix its mistakes and get better? Well, the answer lies in the shape of that cost function and a really elegant mathematical idea called convexity. All right, so let's really think about this. How does an AI find the best possible answer? I mean, it's one thing to know you're wrong, right? But you need a strategy to find what's right. And in machine learning, best means finding the settings, the parameters that give you the smallest possible error, the lowest possible cost. And the best way to get our heads around this search is with a really simple but super powerful analogy. Just imagine that the cost function is a giant, sprawling landscape. Finding the best answer for our model is exactly like a hiker trying to find the absolute lowest point in this entire landscape. Which brings us right to our first section, the search for the minimum. You see, this is the whole point of training a machine learning model. We want to tweak all those parameters until we find the combination that minimizes our cost function. Basically, we're trying to find the very bottom of that valley. And here's the kicker. Whether our hiker's journey is a walk in the park or a total nightmare, it all comes down to one single thing, the shape of this landscape. Is it a simple, smooth valley, or is it a chaotic, treacherous mountain range full of hidden traps? So let's start with the best case scenario, the perfect world. This brings us to section 2, convexity. You can think of it as the perfect valley. This is the kind of shape that makes an AI's job incredibly simple. So, what in the world is a convex function? It's really just a function with a simple, bowl-like shape. The easiest way to picture it is to think of a perfect, smooth salad bowl. It's that simple. No matter where you drop a marble inside that bowl, it's always going to roll down to the exact same single point at the very bottom. And I love how the source material puts it. This isn't just some dry mathematical term. It's described as a beautiful valley. And that really captures the essence of it. It's predictable, it's simple, and it's super easy to navigate for any algorithm. And if there's one thing you take away about convexity, it's this. A convex function has exactly one and only one global minimum. There is just one bottom of the world in this entire landscape. No other tricky spots that kind of look like the bottom but aren't. Just one. So this simple shape gives us something amazing, something we can call the convexity guarantee. You've got this perfect bowl, which means you have one single global minimum. And here's the most important part. Any minimum point you find locally, any little dip you land in, is guaranteed to also be the one and only global minimum. There are no tricks, no false bottoms. But, of course, life isn't always that easy, right? Not all landscapes are perfect. And that brings us to the flip side, the non-convex trap. This is what our hiker and our AI absolutely dreads. A non-convex function is, well, it's the total opposite. It's a chaotic, messy landscape. Picture a rugged mountain range full of all sorts of peaks and valleys. There are tons of little dips and basins. We call those local minima, but only one of them is the absolute lowest point in the whole range, the global minimum. It's so easy to get stuck in one of those smaller valleys, thinking you've reached the bottom when the real bottom is miles away. So let's just put these two side by side to make it super clear. On one hand, you have the convex function, a simple bowl or valley, one single minimum, and a search that's guaranteed to succeed. On the other hand, you have the non-convex function, a complex, chaotic landscape, multiple local minima traps, and a very real risk of getting stuck and never finding the best answer. Okay, so why are we geeking out about valleys and bowls? What's the big deal for machine learning? Well, that leads us right into section 4, the optimizer's guarantee. This is where this math concept has huge, real-world consequences for our AI models. Here's the bottom line. Convexity is like a golden ticket for our optimizer. It provides a powerful mathematical guarantee. It turns what could be an impossibly hard search for the best answer into a problem that we know for a fact we can solve. And the strategy? It couldn't be simpler. You could give these instructions to anyone. Number 1, start anywhere you want in the valley. Doesn't matter where. Number 2, just keep walking downhill. And number 3, you are absolutely 100% guaranteed to arrive at the one true bottom, the global minimum. It's that reliable.
Now let's see how this plays out with some actual real-world models. Some of the foundational models, like linear regression and logistic regression, have convex cost functions. That is awesome. It means for those models, we are guaranteed to find the best possible settings. But then you get to the big guns, like the deep neural networks that power so much of modern AI. Well, their cost surfaces are non-convex, and that means we're not guaranteed to find the absolute best solution. We might just get stuck in a good enough local minimum.
All right, this leads us perfectly into our final piece of the puzzle for today, preparing for the descent. We've talked a lot about the landscape, the what. Now we've got to start thinking about the how. How does our hiker actually know which way to step?
So let's just recap where we are. If we're lucky enough to have a model with a convex cost function, we know we're standing in that beautiful valley. We're on perfect, predictable ground.
And because of that, we have a mathematical certainty. We know with 100% confidence that if we just consistently head downhill, we are guaranteed to find the single lowest point. The destination is assured.
But there's one massive question left, isn't there? It's great to say just walk downhill. But at any given point in this vast landscape, how do we know which way is downhill? How does our algorithm figure out the direction of the steepest slope so it can take its next step?
Well, that method, the secret sauce that tells our algorithm which way to step, the workhorse of optimization in pretty much all of machine learning, has a name. It's called gradient descent. And that, my friends, is exactly what we're going to tear apart in our very next explainer. We're going to dive into the mechanics of the gradient and see precisely how this amazing algorithm lets our models navigate any landscape, convex or not, on their journey to find the minimum. I'll see you then.